Let's look at an elimination problem where we have a primary alcohol that's going to react with H2SO4. So the first step is going to be the alcohol attacking the H from sulfuric acid. Right, so now we've activated the alcohol, but since it was a primary alcohol, we're kind of stuck here. What kind of reactions can we do with the primary alcohol? What can we do? You can only do E2, right? We can't do E1 because we can never form a primary carbocation, right? We can't do it. So if we do E1, or excuse me, E2, we gotta look for our beta H's, right? And you can use this if you want to, but you don't have to use the sulfonate thing to do this elimination. Right, because H2SO4 is the same thing as H plus or H3O plus. They're all the same thing, right?
If it was like HCl.
HCl, HBr is different. Yep. So remember, sulfuric acid, we think eliminations with alcohols. HBr, HI, HCl, we think substitutions, right? And depending on the type of alcohol, primary, secondary, tertiary, the mechanism changes. So here we got an E2. Right? And we've regenerated sulfuric acid, right? Good. So, the problem is this, right? We're always trying to make more substituted, more stable alkenes, right? So if we can make a more substituted alkene, we will, especially in the presence of H+. Right? So this is, even though this is a terminal alkene, it can keep reacting with H2SO4, right? And what kind of carbocation are we going to form? Primary or secondary, do you think? Secondary. And now what kind of alkene are we going to form? A disubstituted or monosubstituted? We're going to want to form a disubstituted. Are we going to want to form a cis alkene or a trans alkene? And now that trans, right? So again, now it's more like an E1 mechanism. But that still gets us to this alkene, this trans alkene that's more substituted. So what's happening is that it just keeps reacting with the H plus available. Okay, so this is one of the retrosynthetic problems from the practice, the last one. Let's take a couple minutes again and just think about some ideas, and we'll throw those out and we'll put those to the side and kind of have it be our initial impressions of this problem. So what ideas do we have? We look at this thing. What are some impressions? Someone said what? Epoxides, perhaps? What else do we have? Anybody?
Leaving groups and alkenes.
I would say leaving groups, alkenes. What else do we have? Add some carbons. Good. We're adding some C's. Anything else? We're making an ether. Trans, maybe? Something about trans. We got have two like an OH and an ether trans to each other. Okay, so now let's do the retrosynthetic analysis. Let's take a step back and say, where is this coming from? So what I will ask you to do now, everyone go to your notes from last Friday. So if you found this in your notes, you should have recognized I have an OH and I have something over here in the less substituted carbon, and they're trans to each other. When I see that the OH and this oxygen, this now ether, are trans, that should set off in your brain OH, something trans, epoxide. If you saw OH and a bromine trans, you should think bromonium ions. Right? But if you see things like this trans, you should think epoxide. So what epoxide did it come from? Came from this epoxide. Right? Came from the epoxide. All right? How do we make epoxides? From an alkene. Good. Had to come from that alkene, right? Where do alkenes come from? How do we make alkenes? We need to have what? Leaving group. And where would it be most likely for this leaving group to be? At this carbon or at this carbon? So it would be likely to be at A or at B. Where would it most likely for where would be most likely for the bromine in this case to be at? A or B?
B.
B. Why?
Most substitute.
It's probably the most likely place it's going to be is because it's the most substituted. Okay? How do we put bromines on rings? Where do they come from? Alkenes again. This one's a challenging one. So it had to come from that alkene. Well, what made that alkene? The bromine being on the benzoic position. All right. Where did that come from? That came from just the alkane. And then we've discussed now Friedel-Crafts, which you should know. So I'm not going to do this because you should know these two steps involving Friedel-Crafts acylation, and reduction. You should know how to do those. So now let's do the forward steps. I'll skip that. If I want to put a 1Br in the benzoic position, what reagents will I use? I'll use light, and what else? And Br2. You could have used MBS, right? Right? The reason MBS would also work because MBS goes for allylic or benzylic radicals, and Br2 just tries to form the most stable radical, right? So what's more stable, a benzylic radical or a tertiary radical then? Benzylic is more stable than tertiary radicals. Okay? So now if I want to do from here to here, what do I need to do? I'm doing a elimination. So what do I need? I would use a bulky base, but not just bulky and a base, but a strong bulky base. You could do E1 here too, because the most stable carbocation is going to be a benzylic carbocation, but don't have to. Right? Now we have this alkene. How do I put the bromine on the less stable position? Actually, you know what? It's more stable. Well, no, it's not. HBr would form a carbocation where? On the benzoic position. So this would be like an anti-Markovnikov type thing. If I want to put a bromine on an anti-Markovnikov position of an alkene, what would I put? HBr and peroxides. Good. Tricky. And maybe you could throw in light, why not? It's fine. Alright? So that was kind of a tricky one right there, where if you did HBr, just HBr, you'd get the bromine back in the benzoic position. But if you do HBr with peroxides, you get it on the anti-Markovnikov, less likely position. Now if I want to do this one, if I want to get the bromine over here, how am I going to do this? This is a tertiary alkyl halide, right? Now I need to make a double bond. That's the non-Zaitsev double bond. So what do I need to use here? Big, bulky, strong base, right? That'll help me get the non-Zaitsev product, right? I don't want to reform this double bond, right? I don't want to do an elimination here. I need to use a big base to prevent that and get the elimination here. Good. Now, from an alkene to form an epoxide, what do? Could use something called an epoxide reagent, which is, of course, right? Should never let that happen, right? Epoxide, no givebacks. Epoxide reagents. At one point, all right, so we got our epoxide reagent, got that done. And then now what do we need to add to get it to go, right? So we need the nucleophile to attack the less substituted carbon. And we need to have, so it needs to be what? Base. So that means basic conditions, which means what charge? Basic conditions means positive or negative charges? Negative charges. So it has to be O minus, and I need to add 2 carbons. That'll attack the less substituted, and that'll get us to the product. So remember talking about essentially Cl dot versus Br dot? And we found out was that Br dot was, you know, somewhere like orders of magnitude more selective. Like more selective is more selective because it was essentially less reactive, right? It's only going to react to form really stable radicals, right? It's only going to react to form really stable radicals. Whereas Cl dot is basically going crazy. It's going to react with everything, right? Cl dot is super reactive. And it's not going to care if you're a primary CH, if you're a secondary CH, or if you're a tertiary. It doesn't care. Br dot is much more selective, right? So Cl dot is super reactive, and it's not very selective. Br dot, right, that's what's nice, right? Because Br dot, we can say, oh, it's going to go for that stable radical. Whereas Cl dot, I don't know where it's going to go. And it might go multiple places at once, right? So that's the biggest problem. And then I dot, right? So why is Cl dot so much more reactive? It's smaller and it can't spread out that deficiency, right? Cl dot's it's smaller, so it's more wound up, literally. I dot, what's wrong with I dot? So I dot's not good either. What's the problem with I dot?
Charge to it.
Now it's not reactive at all, right? There's nothing to it. So it's too big, it's too stable. But then F dot, now F dot is just a mythical figure. It's like a unicorn, right? If it ever did exist, it'd be frightening because it would just react with everything, right? All right, so let's compare and contrast what's going to happen with I did this last night, didn't I? I'm having deja vu. I think I did. Let's do a different one. It's very much the same, that's fine. All right, we're going to add it to tosyl chloride. Right, different ways to activate alcohols. The key with all of these, none of them go through carbocations, right? You do substitutions without going through carbocations. That's the key, right? All right, PBr3. So you attack, kick out the chloride. Pyridine's around. It's hanging out. Right, so this is the tosyl one. Oh gosh. Cl minus. Pyridine takes that H. And the difference between the tosyl ones, we have the S double bond to oxygen twice. Two different ones. The difference is, right, that the Cl minus you still have around, will not do the SN2. Right? You stop right here. You stop here. Right? You have the S double bond to two oxygens, this tosyl, or this is a triflate, whatever you want, whatever. It stops right here. PBr3 is a little different. You attack, right, you kick out a bromine. Pyridine's also around still. All right. Now with this one, it's different. This one, they basically, what happens is, this will keep reacting, and it'll do an SN2 reaction right away. It won't stop. Right, so this did an SN2 right away. Whereas with the tosyl up here, right, I could add in another nucleophile and do an SN2. Right, this isn't a stereocenter. Last night when I did it, these had stereocenters there, and you would have saw, right, if I had a nucleophile here, I'd just do one inversion. If this was R, after I had a nucleophile, it would have stayed R right now. Add a nucleophile, it'd go to S. Here, if this was R, it would go to S, and then if I had a nucleophile, it'd go back to R. Okay, so let's look at there's a bromination, and how we decide if we use Br2 in light, how do we decide where's the Br2 going to end up, where's the bromine going to end up at? Right. So let's look at a couple situations. Right? And we're going to treat this with Br2 and light. Right? Br2 and light. So what's the first step? What's the first step in these reactions? Initiation. Right? So we take our Br, radical, 2 Br dot. Right? It's our initiation step. That's when we first form radicals. Light helps us do that. Our propagation steps is when we take something like Br dot and are going to react it with something else. Right, so now we got to decide what's our weakest CH bond, or where if we put a radical somewhere, what would be the best place to put a radical? Where would be the most stable radical we could put? Right, so
it's a secondary one.
secondary benzylic, right? If you can get something benzylic, do it. Right, just do it.
Even primary benzylic over like tertiary allylic.
I won't make you make that choice. Nobody should have to make that choice, right? I'll make it pretty clear right here, right? There's a benzylic and there's a primary allylic. Right? No, benzylic's better than allylic all the time, right? And notice how there's no CHs here, right? I purposely did that. See what I did there? No CHs. Tricky. All right, so we're all pretty satisfied that this is going to be the place. So again, this is why I emphasize how many electrons in a bond over and over again to you guys. There's always 2 electrons in a bond. So we got 3 electrons in play here, right? So the bromine, one of their electrons, and the electron from the H are going to come together and form a new bond, right? 2 electrons in a bond, and that's what's going to give us HBr. Right? That's where those 2 electrons end up. But be careful, we're not done here, right? Still got to say, where is this other electron going? This other electron's going to the carbon, right? So we got to show that. You have to show that. So there it is. There's the dot. Right? So now what do we need to add there? We've made 2 Br dots. Where are we going to put that Br dot? Well, there's a radical, so what's the final type of a reaction? We can do a termination step. And that's where 2 radicals meet up. When 2 radicals meet up, they stop the reaction. So in this case, we take Br dot. They'd come together, 2 electrons in a bond. And there's your bromine right there. Okay, so here's a diene, 2 alkenes, right? And we're going to treat this with NBS and light or peroxides or whatever. It's NBS. What does NBS tell us? We have bromine, and where are we going to look to add bromines? That's at the allylic CHs, right? So now we look for the allylic CHs. So we know we're going to make radicals at the allylic CHs. So I'll spare you the mechanism part. Right? For every type of allylic CH, we get a type of radical intermediate. Right? So here we have 1 allylic CH. Here's 1, and here's another. Right? There's 2 there, but they're all the same. Right, so there's 2 types of allylic CHs, right? So that means we're at least going to form 2 types of products. But let's, just to be certain, all right, let's draw out the intermediates, because that's going to make a difference, right, for us, because we're going to maybe have some resonance structures we have to deal with here.
Is that one going to happen? Because I thought that it's the same as co-cation stuff.
Well, if I ask you for all possible products, it's possible, right? NBS, we get these allylic radicals, right? So allylic's still pretty stable. Primary is less stable than tertiary, but humor me. I tell you we're gonna make multiple products. Maybe I say we're gonna make. I would do this problem first and actually know how many we're gonna make. I honestly, right now, I have no idea. I know we're making 2, right? There's 2 products right there. So right now we could just go up here and draw, right? Well, I know I'm gonna add bromines, 1 here, right? And I'm gonna have this product as well. Right, I know that. Cool. Now let's draw some resonance structures, see what else we can make. Now it might get trickier for this one on the left. We could draw resonance structures going 2 different directions. You know what would have been helpful here? I'm not going to do it though because I don't think it's that cool. So, no bringing carbons, yeah. No, it's cool. People should be doing it. Don't know why we don't. Electron goes there. 1 goes there, 1 goes there. So that gets us to have a dot there. I could have also had my little dot go this way. Now in this case, this is still good. This is here. Here, boom, boom, right? 2 more intermediates, 2 more resonance structures. So each one of those would have led to a product, right? So we got to put bromines over there too. Those dots. Right? Now we got to go back up to this guy and draw yet 1 more resonance structure. Electron goes there, there. This one goes here. Right? And yet another intermediate is going to lead to another bromination product. So we end up with what, 5? 5 of them. right? So, right, these radical reactions, right, just like carbocations, right? So it's similar to carbocations, right? You can do resonance structures, right? We can start getting lots of different products are possible. Ultimate question: which one of these products is going to be the major product? Which one? I'll label them. Hold on a second. This A. This will be B. C. D. And E. Which one's going to be the major product? A, B, C, or D? So I should label these as well. This is where A came from. This is where C came from. This is where B came from. This is where D came from. This is where E came from. So let's look at it. So let's analyze them. So what does A have going for it? Or which one can we eliminate? Can we eliminate some of these? Just say no. C and which one? B. Right. Why? The primary look. Okay, fine. We've eliminated C and B. Good. I'm agreeing. Is there another one we can eliminate? E. E doesn't have the conjugation. Good. Eliminate E. Now we're stuck with A and D. Those are the two best answers, I would argue. One of them is better. I don't know. Actually, I can argue, right, A is tertiary, but it's not fully conjugated. D is fully conjugated, and it's secondary. So I would guess you'd have a mixture of A and D would be major products. I don't think there'd be really that big of a preference for either one. But certainly, we've narrowed it down to the two best ones, right? For sure. Right? You said conjugation, that makes more sense. That's a good answer. If you said it's doubly, right? A can be resonance stabilized two different ways, so that's good too. I mean, really, in the end of the day, right? Resonance structures aren't real, right? Everybody knows that. It's just like these. There's 1, 2, 5 electrons just spread out between 1, 2, 3, 4, 5 carbons. That's all it really is. So it's just